Last week we learned some of the basics for doing some stoichiometry. We learned about molar ratios. We learned how to calculate molar mass. So today we're going to put all of that together along with the stuff you learned in Unit 5, Unit 4, and so forth and so on back to Unit 1 to do what's called mass-to-mass stoichiometry. So in mass-to-mass stoichiometry, you're going to start with the mass of one substance. And calculate the mass of another substance. That's kind of a simple definition of what mass-to-mass stoichiometry is. It's a pretty simple setup. It might seem complex because there's an awful lot of calculation on the paper, but the basic skeletal setup for the whole thing is really pretty simple. You always start with your starting amount over 1. So we're going to start with the mass of one substance over 1 and a fraction. You're going to calculate the molar mass of that substance that you started with. Build a conversion unit. And convert the starting stuff to moles. And number 3 is we're going to write a balanced equation. Of course, there's a chemical equation we're talking about here. And then we'll use a molar ratio to convert from the substance in steps 1 and 2 to the moles of the substance you want to find. And then we're going to calculate molar mass again, but this time for the second substance. Use that molar mass to build a conversion unit.
Can you slow down?
Would I slow down?
Yes. But I don't know what you're talking about because I'm writing that. I know what you said I'm right.
So these 4 steps are pretty much the 4 steps you'll find in your mole map on page 274 of your text. Why don't you get that out? The mole map. That's what I said, 274. The mole map. Mole map. Mole map. Mole map. All right. Okay. Okay. So in your mole map, you're starting with the mass of substance A. That's what we said here. Then you can build a conversion unit from an equality statement with the sum of the atomic masses of all the atoms in a formula equal to 1 mole. That substance, well, that's molar mass. Okay? Use that conversion then to get the moles of substance A. That's what we're saying here. Okay? Then once you have moles of substance A, use a molar ratio from the coefficients in the balanced chemical equation to get the moles of substance B. That's what we've done in number 3 here. Okay? And then finally, once we have moles of substance B, we calculate a molar mass for substance B. An equality statement built from the sum of the atomic masses of all the atoms in the formula equal to 1 mole of that substance. Using that conversion unit you build from that equality statement, you can get to the mass of substance B. And that's what mass to mass is all about. We're going to go from mass of one substance to mass of another. Okay? And what this also shows you, the mole map shows you, is there's a lot of other conversions and calculations you can do. You can go from number of molecules to some other gas volume, molecules to the mass, from gas volume to number of molecules, and gas volume to mass. You just have to know about the mole to do all that. We talked about that at the very beginning of the unit, that the mole is equal to gas volume at what's called standard temperature and pressure. I think I said that was one atmosphere and 0 degrees C. Okay, so that would allow you to go from gas volume to moles. We said that the mole is equal to 6.02 times 10 to the 23rd particles of a substance. That's Avogadro's number. That's how you get from particles to moles. Okay, so and in fact there are lots of other molar conversions. Later in the semester we'll be learning about solution concentration, and you can do calculations with solution concentration if you're using something called molarity for your concentration. So lots of things the mole can be used for. Right now we're just going to start with mass to mass. Okay? All right. There are several things this mass-to-mass calculation is used for. Actually, we're only going to learn about two of those in this unit. So we use mass-to-mass stoichiometry. We use that to find what's called a limiting reactant. Okay, a limiting reactant. And we use that to find something called the theoretical yield.